Okay, hello everyone, I'm Andrea Caputo and I'm a PhD student here in Valencia with Pilar, and I will be talking about a couple of works and new ideas to detect axion-like particle. And I just tell you that I won't show any results, but actually they are quite interesting, I have to say, so if you want to see them, just come to my poster after this. I just explained the main idea. So let me start with a little bit of introduction, because we didn't hear a lot of talks about the strong CV problem and the axion. We all know that the QCD suffer from this problem. Essentially in the Lagrangian you can put a theta term like this, and even if it is a total derivative, because of the topological structure of the vacuum of SU3, essentially you can have observable effect, and you predict a dipole moment for the neutron, for which we just have bounds. And this essentially turns out into a constraint for this theta term that is a dimensionless parameter that has to be very small. And we would like to have an explanation why this parameter is very small. A very elegant solution to this is the axion, at least in my opinion. And the idea is that you introduce a new symmetry that is broken, that is the U1 global phase-sequence symmetry, and then you have the promotion of the theta term to a dynamical field that is the axion. That is a pseudo-Goldstone boson that turns out quite easily to be a very good dark matter candidate. So for my talk, the two ideas that I will be discussing, the fact that it's a dark matter candidate is crucial. And it's crucial also that if you perform a chiral transformation, essentially you can end up with a coupling of the axion, not with a gluon, but with a photon. So in both way, both technique, I will use the coupling with a photon. So the first idea is very simple, and essentially you have your axion, and through the anomalous diagram, it will decay into two photons. Each of the photons will have an energy that is just half the mass of the axion, because this is just decay. And so the observation will be very clear. Essentially, you will be looking for a photon at a given frequency that is given by once that you fix the mass of the axion. The only issue with this is that essentially, if you compute a lifetime, it depends on the mass of the axion and on the coupling with the photon, and if you plug in some typical QCD axion numbers, you get a lifetime that is huge, much larger than the age of the universe. And this is why people usually neglected it, thinking that it was crazy to look for this. But with Sam actually and with our other collaborators, we were crazy enough to try to estimate this. From this picture you can understand two things. First of all, I'm not good at drawing. Second of all, the target here are astrophysical target. So you look, for example, at a dwarf galaxy or a galactic center, and you assume that it will be made by axion dark matter. And some of them will decay through the anomalous diagram into photons. Then you point your telescope to this target, and you're looking for this photon at a very precise frequency. And you can compute the flux that you expect for the decay, and it will depend on the rate of the decay and on the density of the axion dark matter that you have. And also this other factor that is more tricky is a stimulated emission factor, and if you want to know more about this, ask me later. And essentially you can compare this with the sensitivity of SKA, for example, and get your bound. And I just to tell you, we can get bound that are better by 1 order of magnitude respect to cast in the QCD in a given mass range. And then I just introduced my second technique. It's a completely different technique, but it's related always to the coupling with the photon. This is very nice. So we use pulsar polarization measurement. So pulsar, they are neutron star, they emit a very precise signal, that photon signal, electromagnetic wave, with a precise timing and period. And we observe it for a very long time. So we can observe a pulsar for a year, 10 years or whatever. We can measure the polarization, the period, the spectrum of the signal. Then now imagine that this signal is traveling into a medium of dark matter that is made of axion-like particle, a medium that is oscillating. So what happens when you put this coupling, this axion field here, is that your Maxwell equations are just modified. You have this source term here. And what happens is that also the dispersion relation of the photon that is traveling into this medium of particle is changing. And it's changing in such a way that essentially right and left-handed mode, they propagate with different speed. And this is just because, the interaction is parity violating. And this causes essentially the plane of polarization to rotate, but actually it's not just a rotation like a simple Faraday rotation, it's an oscillation. And so this is theta, is not a theta term, is the polarization angle of the signal that you are detecting from your pulsar. And it will be oscillating with a frequency that is given by the mass of the axion medium. So notice here that the mass that I'm probing with this second technique is like very small. This is what people call fuzzy dark matter. So you have this photon traveling into this medium that is oscillating, and you can look for this pattern into the data. And we look to the data, so the one that I will show are real bounds, and are actually the strongest one in some interesting mass range for the fuzzy dark matter. And I invite you to my poster, and I thank you all for the attention. And if you have any questions, just ask me.
Thank you very much. Questions?
Are there any well-aligned pulsars that have likelihood to have their beam go through some interesting axion region?
Yeah, I mean, actually, this is a very important question, because actually, if you compute the fact, this is not very important, like the region of the axion in which like the photon propagate. It depends just because like at the end is a total derivative, the coupling that enter into the equation. Essentially, the effect will depend just on the relic abundance of the axion where the pulsar is located, and the relic abundance, the local relic abundance when we detect the signal. And actually, for example, for the pulsar that we were using, it was like a very close pulsar, like 150 kiloparsec. So it was just the local density of dark matter. So we don't need to have this effect, we don't need a huge caustic or whatever. It's just normal density. Yeah.
Can you say again, I missed the connection with the fuzzy dark matter?
Yeah. The point is that essentially in this calculation, so you just assume that it's fuzzy dark matter with a normal density, and the effect is not negligible even if you assume just local density, and it's not like, the effect is not affected by the profile density in between the pulsar and us. Because at the end, if you look at if you solve essentially the equation, the coupling always enters with a derivative. So at the end, it will just depend on the density at the beginning of when you emit your signal and at the end.
So this has nothing to do with UCD axion that you
In fact, this is a good question also, because my title is axion-like particle. This is the less QCD that I have in my talk. So the first part is like more QCD-like, even if we don't touch band, but it's like fuzzy dark matter with this coupling, yeah.
Okay, so let's thank the speaker.